Okay, this is my PN junction. So this is my PN junction where the P has a doping concentration higher than the N. And of course, this is a situation when we have applied a voltage. So this is a forward bias condition and we have applied a voltage, and because of which the depletion width has become smaller and there is a diffusion current ID in this direction. And this diffusion current ID, of course, is much greater than the other current IS, which is flowing in this direction. So, and this is much greater than this one. So now we want to find out the equation of this ID. Okay, and this is of course in forward bias condition. We will derive the characteristic equation of this diode in the forward bias condition, and the same formula can be applied for the reverse bias condition as well. This has the carrier concentration in this case has Na. So the holes concentration in this case is Na. Okay. Electrons, which is the majority carriers in the N side, has a concentration of Nd. Okay. So now it has a minority charge carrier, right? So when the voltage was not applied, let's call the minority charge carrier concentration, in this case it's electrons. So let's call the minority charge carrier as, in this case it's electron on the p side. Let's call it as 0, and this is equal to Ni square by Na. This is in the equilibrium conditions, and in this case the holes has a concentration of P on the N0, again Ni square by Nd. So this is what we know. So this is the minority charge carrier concentration. This was the situation when V was 0. Okay. So now slowly we have increased this V, and because of which this depletion width has reduced, this W has reduced, this becomes smaller, and there will be diffusion current, more diffusion current. These holes will be diffused here, right? So as a result of which the minority charge carrier here is going to be greater than this value, which was in the equilibrium condition when no voltage was applied. So this is because of the thermal generation. Now what will happen is more number of these holes are going to get diffused this side. Similarly, more number of electrons are going to get diffused this side. So this is what we are going to study now. So to study this one more elaborately, let's draw this graph of the minority charge carriers. So this is my x, and in my y-axis I'm going to represent only the minority charge carrier. Okay. So in the y-axis I'm going to represent the minority charge carrier concentration. So of course this is my depletion region. Okay. This is 0, this is my xn, this is my xp. Okay, so now initially when there was no voltage applied, no forward bias applied, we know that this is this region. Okay, this is the pn0. Okay, so which is Ni square by Nd, and in this case of course this will be smaller. This is smaller because we know that these Na is greater than Nd, so the minority charge carrier concentration in this case is smaller. Okay, so this was the level. So this was the situation when there was no forward bias voltage applied. Okay, so now we have applied a forward bias voltage, and because of which these holes will get diffused to this side, and as a result of which, if you see in this N side, the minority charge carrier concentration is going to increase. Okay, so let's call the increase, maybe let's call it has increased to the to this point. Okay, to this point, and now we have an excess amount of holes here, so let's call it as EP, excess holes, EP, E for excess and P is for holes. Okay, so now we want to find out how much is this excess amount of holes here. Okay, and also along with this, we know that the barrier potential in this case has reduced, right? If you see the barrier potential for no voltage applied, we know that it is V0, and now it has become V0 minus V, okay? Because a forward bias voltage of V is applied. So now to find out this one, to find out this excess, we need to find out what is the total carrier concentration here, which is, let's call it as the holes at distance xn, okay? So we want to find out the total holes at the n side and at distance xn, okay, from 0. Okay, so we want to find it out. So to find this value, we will again use the equation that we have used. We'll again one of the equation which we have used to find out the built-in potential. So if you go back to the previous lecture discussion, so this is the derivation of the barrier potential, and we have equated the I drift with the I diffusion, and finally we have got this kind of expression, right? That the potential difference between the V of x of n minus V of minus xv is equal to this one. So let's write this equation, okay? Okay, so this was the expression which we have derived in the last class, that the potential difference between this point and this point, of course we have made it as V naught, or the built-in potential when no voltage is applied, so is equal to Vt Ln, is the concentration of the holes at this boundary, which is Pp, and concentration of the holes on this n side at this boundary, which is Pn. Okay, so to be more precise, let's write it as at a location of minus xp, the concentration of the holes on the n side at a location of xn. Okay, so yeah, so here what we want to find out is the concentration of the holes here at this point, right? So this is what we want to find it out. Okay, so now we know that the potential difference between this point and this point has become V naught minus V, because I have applied a forward bias voltage of V, is equal to Vt ln, and we know the concentration of the holes at this site is still given by, you know, this Na, so I can write it as Na. Okay, and of course I want to find the minority charge carrier Pn at Xn. Okay, so now let's rearrange this equation a little bit. So I can multiply negative on both sides, and this will get inverse. Okay, and this will become V minus V naught. So finally what I'll get is, if I just rearrange this simple equation or the simple mathematics, it will be something like this. This Vt will go down and Ln will become exponential. So it will be V minus V naught by Vt. Finally, what I'll get here is Pn of Xn will be equal to Na e power. I can expand this one as V by Vt minus V naught by Vt. Okay, so this is my equation number 1. Okay, and we know that V naught is equal to Vt ln Na Nd by Ni square. Again, if I rearrange this equation, right, so what I'll do is I will multiply -1 on both sides, this one, so it will become minus V naught will be equal to Vt ln Ni square will come up, so Ni square by Nd into 1 by Na. Okay, now we know that this term Ni square by Nd, if you see here, this is Pn0. So this is the concentration of the holes on this side when the no voltage was applied. Okay, basically this line. Okay, so if I rearrange it, what I will get here is the Vt will come here down and Ln will become exponential, and this term will become Pn0. Okay, so finally what I will get here is the Pn0 will be equal to Na e power minus P0 by Vt. Okay, so this is equation number 2. So if you see in the equation number 1, this Na into e power minus V0 by Vt, right? Na into e power V0 by Vt minus V0 by Vt can be replaced by Pn0. Okay, so these two whole terms can be written by Pn0. So from 1 and 2, so what it means is, if I have applied a voltage V in the forward bias condition, the concentration of the minority carriers at this point, which is this one, will be equal to Pn0. This is equal to Pn0, which is the concentration of the minority carriers when no voltage is applied, into e power V by Vt. So it is the minority charge carrier here is going to increase exponentially with increase in the applied voltage. Okay, so this is what it means. Okay, so now if I know the carrier concentration here at this point, which is Pnxn, so I can easily find out this concentration of the excess carrier, which is basically the difference of Pnxn minus this Pn0. So the excess okay, or I can write it as Pn0 e power V by Vt minus 1. Okay, so this much amount of excess concentration has occurred. Okay, so now the question is, what will happen to this? So the question here is, what will happen to the minority charge carrier concentration that has come? Is that all they are going to get diffused? No. So what is going to happen is, whatever the minority charge carrier is diffused this side, they are going to decay basically. So their profile is going to become something like this. They are going to decay as it goes along this side, and and they are going to decay exponentially, and this function will be given by, I can write, so p of nx, right? I can have a simple function. So this function is basically exponentially decaying. Okay, and of course this is a value at this point, which is Pnxn. Okay, this is the function of the minority holes, okay, which is Pnx. Okay, yeah, and this is exponentially decaying. Okay, so I can write this function Pnx as, so the excess minority carrier will decay exponentially. This excess minority charge carrier will decay exponentially, and we can write Pnx, the concentration of the holes on n side with the variation of x, with x-axis as a variable, can be written as Pn0, because this is the base, right? Pn0 plus Ep into the exponential decay function, Pn0 plus the excess carrier, which is holes, and it will decay exponentially, but then it will start from minus xn. So the whole things get shifted by xn, right? It starts from here, so it will start from the xn. So that's why x minus xn. The curve has shifted from 0 to here. So, and it is decaying exponentially. But now the question is, how fast is the decay? How to define how fast is the decay? Is it something like this, or is it very fast, or is it very slow? Okay, so to define how fast it is decaying, we have to introduce a constant. Okay, just like in an RC time constant, like we know that exponentially it is decaying, but tau, right, tau equal to RC defines how fast the charge is discharging in a RC circuit. So similarly, there is a constant which is this constant LP, right? This defines how fast the holes are decaying as it goes towards X. Okay, so where my LP is a constant called diffusion length of the holes in N-type material. So now if there is a variation in the concentration, right, we know that there will be a diffusion current. So this profile will lead to a diffusion current, and we know what's the formula of the diffusion current. So and the diffusion current, the diffusion current density Jpx, we know that it is given by minus q dp dp and x by dx. So this is the standard formula which we have discussed for the diffusion current, right? So we have this again, the diffusion constant, and this we need to differentiate the profile of the change in the concentration of the carriers. Okay, so now if I just differentiate this one with respect to x, what I'll get is this will become 0, and of course this is also is not dependent on x, right? So I can just differentiate this term. So this minus 1 by LP will come in the front, implies my Jp x will come to be minus q dp ep, and this LP will come, and this minus minus will get cancelled, so I can remove this negative term. Okay, now I can replace this value of EP. We know that EP is given by this one. Okay, I have replaced the value of the EP, and this is, of course, okay. So if you see this current term, you see it is maximum at x equal to xn. Okay, of course it cannot be less than xn because the curve starts from x equal to xn, and as x increases we can see that it decreases. So it is maximum at x equal to xn. So let's try to find out the Jp at x equal to xn. Okay, so we have found this term, so which is the maximum diffusion current, and it is maximum at x equal to xn. So what it means is my diffusion current, whatever I have derived, is maximum at this point. Okay, so it is maximum at this point, but the question arises is then how come, like what will be its value? So its value is smaller here and its value is maximum here, but this is not possible because you see if I draw a cross section here, the current should be same here also and here also, in fact everywhere. Even if I draw a cross section here, the amount of charge that is flowing here, that is flowing here, it should be same, because according to the KCL, right, we cannot create or we cannot destruct a current, right? So then how it's true, right? So basically what is happening is the holes are getting diffused here, and as the holes goes this side, the electrons will come from the battery, right, and it will try to recombine with these holes. As a result, there is a decay in the concentration. Okay, so so because of which it will lead to a current conduction in this direction. Okay, because the electrons are flowing in this direction, holes are coming, they are recombining. Okay, but if you see here, at this point it has not yet recombined. Okay, So here at this point the holes has just arrived diffused from this side, okay, but as it goes ahead it starts recombination. Okay, so here we have two kinds of current. One is the diffusion current as well as the recombination current with the electrons. Okay, but only at here we have the diffusion current component. Okay, so if I try to find out the current here, which is basically on the diffusion current, so that means whatever the current that we have evaluated here at x equal to xn, the diffusion current is the actual current of the flow of the holes in this direction. So this current density is the current due to the flow of the holes, right, which is through the wear or in other cross section as well. So similar to the diffusion of the holes in this side, there will be diffusion of the electrons in the other side from here to here, and I am going to get similar curve something like this, which I can call it as the electrons, which is n on the p side and nx. Okay, so I can do similar kind of derivation on the for the electrons, and I will get similar kind of current density, which is in a maximum here, and this is only the diffusion current. Okay, so again I can write this one. I can write the current density of the diffusion current here. So similarly on the p side we will get the Jn due to the electrons at minus xp is maximum is given by d of q into d of ln p, and p0 e power v by vt minus 1. So it will be exactly opposite, right? dn dp lp will be replaced by dn ln, and pn0 will be replaced by np0. Okay, so the total current will basically constitute these two due to the holes as well as due to the electron. So the total current J, right, total current J will be the summation of these two, J minus xp, and therefore my I just need to multiply with the area. So I can this is AJ, right, AJ, and if I substitute this J with this and with whatever the terms that I have here, so what finally what I'll get here is and we know that Pn0 is the concentration of the holes in the n side when there is no electric field. And this np0 is equal to ni squared by na. Okay, so if I just substitute this, finally what I'll get is, therefore my I will be equal to q ni squared dp lp by nd dn ln So this is my final expression of the current, diode current. Okay, so this term is called as the IS term. So what I can write is I is equal to IS into e power t minus 1, where my IS is equal to AQ ni squared Okay, so this is the final diode equation where IS is also called the reverse saturation current. Okay, so because if you see here, if this V is much negative, this is going to become 0, so it's going to become minus IS, so which is the reverse saturation current. And in the forward bias current, of course, in the forward condition, so this is going to give me the current for the diode.